Yesterday we learned a little bit about projectile motion. When we talk about projectile motion, we didn't know what a projectile is, right? Projectile is anything that moves through the air under the influence of just gravity. A projectile could take a path that looks something like this, maybe off the edge of a building or the edge of a cliff. Maybe it takes a path that looks like this. Soccer ball is kicked from ground level, goes up like this, comes back down to ground level. Maybe it takes a path like this. A basketball is thrown from this level and then goes into a hoop that's at this level. The bottom line is, in all three cases, even though the path is a little bit different, the problem is a little bit different, the shape of each path is what? It's a parabola, right? This is a parabola. It's like a half parabola. This is like a, I don't know, 2/3 parabola, something like that, whatever. This is a full parabola. Okay, we have a parabola in all three cases here. Now, because we have a parabola, it means it's not in one dimension. It's a two-dimensional problem, right? Two-dimensional problems means we've got to break it up into x components and y components. All three of these cases, we'd say x and y, and in all three of these cases, we'd say delta d over delta t for the x component because it's traveling at a constant velocity horizontally, and we'd say d is equal to vit plus 1/2 at squared for the y component. Really, it's any acceleration equation, but this one happens to work for us most often. Now, yesterday we learned how to apply those two equations to this problem. Today, we're going to learn how to apply them to the other situations that we saw drawn up on the board there. But let's focus right now on what we had last night for homework, which is a problem like you see up on the board right now. Okay, the velocity, whatever we have here. We don't know displacement, we don't know time. The displacement for the y component would be whatever the height of the building is. Okay, acceleration, VI would be 0 because it's launched horizontally. The acceleration would be negative 9.81 meters per second squared. General strategy is this. Okay, get something. Write down what we have written down here. Plug in your numbers, solve for something. If it happens to be, if you happen to be able to solve for what you're looking for right off the top, that's great. If you don't, that's fine. Just get something and then use it to find something else. What you'll often get first, honestly, is time. That's rarely what you're actually looking for. What you usually get first is time. Usually you're going to use that time to solve for a displacement or a velocity or something like that. All right. We had 3 questions for homework on page 107. I want to take a look at number 3 on page 107. Number 3, because the setup of it is exactly the same as the example we did yesterday, but we're solving for a different variable here. So let's start that off by drawing the picture. Here's the cliff. It's 100 meters high. We know that this object is launched horizontally off the edge of the cliff, and we know that it follows a parabolic path as it falls down toward the ground, and we know that it lands 40 meters from the ground. In the last class, period 2, I said, what are you going to do first? Somebody said, write down the givens. Yes, write down givens. But you know what? I've pretty much got those written down already, right? They're pretty much there already. What else am I going to do first beyond the givens, beyond the picture? Write down your equations. Okay? X components, Y components. Let's say V is equal to delta D over delta T, always for the X component. D is equal to VIT plus 1/2 AT squared. Technically, that's not always what we'll use for the Y component because there's other acceleration equations as well. But you know what? That's always what you're going to try. Okay? Do that first. Okay? And it's going to work for you 99.9% of the time. Now we plug numbers in. Unlike the example we did yesterday, we don't know what V is for the X component. We know what D is this time, though. It's 40 meters. We don't know what D is. So yesterday when we did the example, we had 2 unknowns. We still do. It's just 2 different unknowns. Y component, displacement is negative 100 because it ends up 100 below where it started. VI is 0. We don't know what its initial velocity is, but we know it's all x because it tells us it's launched horizontal. Plus 1/2 times neg 9.81 times t squared. Let's simplify this a little bit. 1/2 times neg 9.81, neg 4.905. let's take the 4.905 over by dividing. We do that. 100 divided by 4.905 gives me 20.4. Square root that. 4.515. All right. I wasn't looking for how long this ball's in the air for, but I found it. That's okay. It's not the answer I'm looking for, but it's correct so far. What are we going to do with this time now? Yep. Yeah, displacement divided by it, yeah. So 40 meters divided by 4.515. And we get 8.9. It should be 3 digits, I think 8.86. Good. How is this similar to the question we did yesterday? Well, the diagram looks almost exactly the same, right? We set up X and Y components. We set up the same equations. The strategy is the same. Plug in your numbers and solve for something. How's it different? Well, we have a different variable. Still solve for t first. Still plug it back into this equation, except that this time we have d instead of v. Strategically, it doesn't change a thing. Strategically, it's the exact same question as yesterday. It's just the little finer points of the question that we have to alter a little bit from yesterday. How is that? Good. That's question number, basically, that's question number 7, right, on the assignment that I gave you that's due on Monday. All right. I want to do a question like number 8 on your assignment now. Number 8 on your assignment has, I forget the context of it, but it's something like this. You have a, let's say you have a soccer ball. We kick it at an angle of 30 degrees at a speed of 10 meters per second. And let's say that it goes up here, goes back down, follows a parabolic path again, but this time it's a full parabola, lands somewhere downfield. We want to find out how far downfield it ends up. Besides your givens, which we pretty much already have written down, what's the first thing you think of when you see this? I'll accept 2 answers here, by the way. Because whether you think of these as step 1 and step 2, or step 2, step 1, it doesn't really matter which one you do first. Okay, what's the first thing that you think of, Andres? I don't like funny angles, okay? I don't like funny angles, that's 1. So let's get rid of it. Let's take it off to the side, and let's get rid of that funny angle. Just because this question is a completely different context than the questions we did earlier in the week and last week, doesn't make any difference. If we see a funny angle, we don't like it, we get rid of it. It's going to happen a lot next year in Physics 30, in completely different contexts still. Whenever you see a funny angle, get rid of it. All right, let's say cosine 30 degrees is equal to adjacent over hypotenuse. Sine 30 degrees is equal to opposite over hypotenuse. Let's square that off. Take it off to the side. And now, the other thing that I would have accepted for the first thing that you think of is, well, whenever you see a projectile motion question, it's X and Y components, right? And my equations, V is equal to delta D over delta T, and D is equal to VIT plus 1/2 AT squared. Hey, what's V? For the X component, that is, what's V? Is it? Nope. Yep. 8.66. All right, the 10 is gone now. The 10 is dead to us now. So we're not paying any attention to that 10 meters per second anymore. That 10 meters per second became 8.6 and 5. The X component is 8.6, so plug it in. Delta D, we don't know. Delta T, we don't know. All right. So we're encountering a similar problem that we encountered with our example problem and the problem we just did here from homework last night. That's okay. 2 unknowns is fine. Let's go over to the Y component. Who could tell me what delta D is for the Y component? Who could tell me what delta D is? Yep. 0. Good. It's good. Horizontally, it starts here and ends here. But vertically, it starts here and ends here, vertically. It ends up at the same height, right? So let's make delta t 0. The I is 5. The y component of it times t plus 1/2 negative 9.81 times t squared. Let's simplify this a little bit. Half of negative 9.81 is negative 4.905. And now let's take, you don't have to do this, but it makes it a little bit easier to solve. I'm going to take this over to the other side. It becomes positive 4.905t squared equals 5t. You can divide both sides by t. When you do that, one of these t's disappears, and that t disappears. So it becomes 4.905t equals 5. 5 divided by 4.905, 1.0194. Which we're going to turn on and plug back into there, right? How come we can do that? I've asked you this question a bunch. You guys nailed it the first time I asked you. Good, times the scalar. So let's say 8.66 now times 1.0194 gives me 8.82, or we'll say delta D is 8.8 meters. How far downfield does the football, or sorry, does the soccer ball land? 8.8 meters. Who plays soccer here? Nobody? Oh, Mattis? Okay. Get a feeling that normally you can probably kick it more than 8.8 meters. That's not very far. But if you're only kicking it at 10 meters per second at 30 degrees, that's all you're going to kick it, right? We're going to give you one question to work on for the last little bit in class here. Here's an object that's launched at 20 meters per second. Let's call it a football. It's kicked at 20 meters per second at an angle of 40 degrees. We want to know how far downfield it ends up going. Okay, what is that question mark value there? How far downfield does it go before it lands on the ground? All right, let's have a look, guys. First thing we see a funny angle. We want to get rid of that funny angle. So let's take that up here, 20 meters per second. We got an angle of 40 degrees inside the triangle here. This is X, this is Y. We'll say cosine 40 degrees is equal to adjacent over hypotenuse. And we'll say sine 40 degrees is equal to opposite over hypotenuse. What do we end up getting for X there? 20 cos 40 is 17.3 meters per second. And what's the Y component there? 20 sine 40? 12.86, thank you. Is that wrong? 15.32? All right. There we go. Let's go over here now and do our X components and our Y components. We're going to say for the X component, V is equal to delta D over delta T.